All right, today we're going to pull back the curtain on the secret language of movement, geometric transformations. Now, this might sound complicated, but I promise you, it's not. From the pixels on your screen to planets in orbit, these simple rules are basically the code that describes how everything moves and changes. You ready to crack it? Let's dive in. Okay, picture this. You're in a massive, sprawling library. You need to find one specific book. A librarian, super busy, just gives you two numbers, 4 and 5. And with just those two numbers, you can walk right to the exact spot, shelf 4, row 5. It's simple, right? But it only works because there's a system in place. And that, right there, opens up a much bigger question. How do we give a precise location for anything? I mean, whether it's finding that book, guiding a massive ship through the ocean, or programming the entire world of a video game, you absolutely need a universal map. Well, in the world of math, we have that map. It's called the Cartesian plane. You've probably seen it before. It's our grid for giving everything an exact address. The first number, that's the x-coordinate, tells you how far to go across, left or right. And the second number, the y-coordinate, tells you how far to go up or down. This grid, this is the stage where all the magic is about to happen. So, this is our map for math. It's the foundation, the very bedrock for the 4 incredible transformations we're about to explore. First up, let's start with the simplest move in the book, the slide. Or, as mathematicians like to call it, a translation. You know, the best way to get this is to think about a chess piece. When you slide your knight across the board, it's still a knight, right? It hasn't changed its shape, its size, or even which way it's facing. The only thing you've changed is its location. That's literally what's happening when a video game character just slides across your screen. And that's the official definition. A translation is just a transformation that slides every single point of a shape the exact same distance and in the exact same direction. And here's the absolute key. Nothing else changes. No flipping, no turning, no resizing. It's just a simple slide.
Okay, but here's where the magic really happens. We can track this movement with total precision. Take a look at this shape. It started down in the bottom left and then just slid all the way up to the top right. It's the same shape, just with a new address on our grid. But how exactly did it get there? See, this isn't just random movement. There's a rule, a simple, predictable pattern. If we look at just one corner, or vertex, it moved from -2, all the way to 7, 11. So how did it do that? The rule was simple. Add 9 to its x value and add 13 to its y value. And that exact same rule was applied to every single point on that shape.
All right, so that's the slide. Super simple. But what if you want to create a mirror image? Well, that's where our next transformation comes in, the flip, also known as a reflection. A reflection is exactly what it sounds like. It's a perfect flip across a line. We call that the mirror line, or the line of reflection. The new shape is a perfect but reverse copy of the original. This is totally essential for creating all the symmetry we see in art and design. And the #1 rule for reflections? It's all about distance. Every single point on the new reflected shape is the exact same distance from that mirror line as its original point, just on the opposite side. Okay, let's actually see what this looks like. Here, we're flipping a triangle across the vertical y-axis. See that? The shape on the right is a perfect mirror image of the one on the left. It's almost like it's looking at itself in a mirror. And you guessed it, there's a simple code for the coordinates here too. When you reflect across that vertical y-axis, the height, the y-coordinate, doesn't change at all, but the horizontal position, the x-coordinate, it just flips to its opposite. So a point at -15 on the x-axis jumps right over to +15. All right, so we've slid, we've flipped. What's left? A turn, of course. In geometry, we call this rotation. You know, the absolute best analogy for a rotation is a combination lock. When you're spinning that dial, all the numbers are cruising around in a circle, but there's that one spot right in the dead center that doesn't move an inch. That's the anchor for the whole turn, just like the center of a spinning wheel in an animation. So to pull off a perfect rotation, you need the recipe. And there are only 3 ingredients. First, the center of rotation. That's the fixed point you turn around. Second, the direction. Are you going clockwise or counterclockwise? And third, the angle. How far are you turning? A quarter turn is 90 degrees. A half turn is 180. You get the idea. Let's actually do one. we're going to take this triangle and rotate it 90 degrees clockwise. And we're going to do it around the origin. That's our center point at 0, 0. You can see how the entire shape just pivots around that central spot.
Okay, I'll admit the coordinate pattern for a rotation can seem a little tricky at first, but there's a simple rule. For a 90-degree clockwise turn, two things happen. First, the x and y coordinates literally swap places. Then the new y coordinate flips its sign, so a point that starts at 1, 7 ends up at 7, negative 1. It's a predictable little mathematical dance.
We've slid, we've flipped, and we've turned. We're almost there. But what about changing the size? Well, that's our final transformation, the resize, or dilation. The best way to think about this is like an architect's blueprint. The blueprint is a perfect but small version of the final building. Dilation is basically the process of scaling that blueprint up to full size. The shape stays exactly the same, but the size is totally different. And we measure that change with something called a scale factor. So, in a nutshell, dilation is a transformation that either makes a figure bigger, an enlargement, or smaller, a reduction. If the scale factor is more than 1, it gets bigger. If it's less than 1, like when you pinch to zoom out on a map on your phone, it gets smaller. But the crucial part is the proportions, the overall shape, stay exactly the same. And the math for this, honestly, it's the easiest one of the bunch. To dilate a shape from the origin, you just multiply every single coordinate, both the x and the y, by that scale factor. You want to make it twice as big? You just multiply everything by 2. It is that simple. So let's step back for a second. What does this all mean when we put it all together? Well, we've just learned the 4 key elements of a really powerful geometric code.
Translation, that's the slide. Reflection, the flip. Rotation, the turn. And dilation, the resize. These 4 simple moves, they're the building blocks, the alphabet of a powerful mathematical language. One that can describe pretty much any movement or change you can imagine on a flat surface.
And why should you care? Because this isn't just stuff for a math class. This is the secret code running underneath so much of our modern world. I mean, think about it. Animators use these transformations to bring characters to life. Video game engines use them to move your character through these huge digital worlds. And robotic arms use them to perform incredibly precise tasks in factories. Every single time you watch a cartoon, play a game, or even just see a graphic move on a screen, you are watching this code in action. And now that you know the code, you're going to start seeing it everywhere. I guarantee it. So my question to you is, where are you going to spot it first? The world around you is just full of these hidden patterns waiting for you to find them.